looking for planets, Earth-like planets in the Alpha Centauri system. And then one of the questions that I get nowadays from people in the press is, okay, Deborah, we've heard yet one more first Earth ever detected, most habitable, whatever. Tell me what it is that makes a planet habitable. So I thought I might share that idea with you. And then also, we can now look back and answer a question that we had no idea about 15 years ago. And that's, how does our solar system compare? Anybody have any ideas? Are we normal? Typical? Copernicus would say, right? Copernicus would say that, no, we hear a no. All right, you guys should move in. I can tell she's going to be good. All right, future astronomer. Okay, and then I want to come to the point that I think is really important at the end, that why I think astronomy is important and valuable, and why I do this work, and I hope that you guys are interested in it as well. Okay, so first of all, our place in space, and I have to apologize because we had, as you saw, we had a last-minute scramble, and so it's pretty clear to me that not everything in this presentation is going to work, but I think together we can still get through this. Okay, so our solar system, we live on this little tiny planet here orbiting the sun, right? There are 8 planets in our solar system now that Pluto's been demoted. And there's a lot of rocky debris, as you know, right? A lot of leftover material from the time when the planets formed in our solar system. We know that most planets have moons. I don't know what this one was supposed to be, but one thing is missing. Yeah, exactly, it's a moon. And that the planets in our solar system are on nearly circular orbits. And only one of these 8 planets is inhabited, although we're looking for signs of life, and maybe life someplace else, like on one of the moons around Jupiter, for example. So these are the things that, because remember in the end we're going to come back to how does our solar system compare, and so we'll come back to this slide, in fact. Zooming out from our solar system, our place in space, remember, if you look at the entire Milky Way galaxy, here's a field of stars, and our sun is a fairly normal star, a fairly unremarkable star. It's one of, it says millions, but billions, okay? 200 to 400 billion stars in the Milky Way galaxy. And then our galaxy is just one of another, hundreds of billions of galaxies in the universe. All right, so that's a concept that's just sort of blows your mind, to think that the Earth, everything we know, is this tiny little speck of dust around just a normal star, which is just one of billions of stars in our galaxy, which is one of billions of galaxies in the universe. And here's a picture, from the Hubble Space Telescope. The universe contains, billions, trillions of galaxies. And you see this incredibly rich field. There's another amazing image from Hubble, the Hubble Deep Field, where the Hubble Space Telescope was instructed to, why don't you go to this place? It's kind of over near the Big Dipper. And the reason we're interested is because astronomers have looked there, and with our strongest, most powerful telescopes, we see nothing. And so for 3 weeks, the Hubble Space Telescope would go back. And I'm going like this because how long does it take the Hubble Space Telescope to go around the Earth? One orbit, exactly, 90 minutes, right? And so imagine taking a picture. You have to zoom around, snap, snap. So it integrated open shutter time for 3 weeks, okay, in total, and discovered this amazing image with something like 10,000 galaxies, distant galaxies, in this part of the sky where we thought there was nothing. Okay, there was nothing to obstruct our view. So that was the kind of interesting thing. Okay, so that's our place in space, which is pretty humbling. All right, but then what about our place in time? Like, we're pretty important. We've been here forever, right? Well, time is it's hard to sort of wrap your mind around this idea as well. And so Carl Sagan came up with something called a cosmic calendar, which was brilliant, because everybody knows what 1 year feels like. And so he scaled this 13.65 billion years, okay, that the universe has existed. He scaled it to 1 year. And he said, on January 1st, clock ticks over, Big Bang occurs. And now we're at December 31st. The clock is just about to tick over to the next year. And then during this year, what happened in terms of the formation of the galaxy, our solar system, and so on? Well, it turns out that, around May, the Milky Way galaxy formed. Before that, there were little proto-galaxies that were accumulating, forming bigger galaxies. It wasn't until August in this cosmic calendar that our solar system even formed, okay? And then already, though, by September, we think that the first signs of life appeared on our planet. So that's pretty incredible. Now if you go back and you sort of look in, okay, September, now let's jump to December. Now you should be getting a little bit worried because it's not until around December 25th that the dinosaurs, the beloved dinosaurs, appeared, right? And they lasted for 7 days on the cosmic calendar. Right, wait, let's count that. 1, 2, 3, 4, 5, 6. 6 days. Okay, 6 days on the cosmic calendar. So, but now it's December 30th, right? And the dinosaurs are just going extinct. So where does that leave us? Well, we have to zoom into the last 60 seconds, it turns out. Okay, in the last 60 seconds, humans migrate to the Americas. 15 seconds ago, the first cities appear in Mesopotamia. Let's see, Christ was born 5 seconds ago, actually a little less than 5 seconds. Columbus arrives in America 1 second before midnight. Okay, so in this cosmic year, okay, we occupy the last fraction, the last few seconds of the entire year. All right, so there you are. Now that you all feel very important, we'll come back to this idea because we are very important, okay? So I want to tell you a little bit about the techniques that we're using to find other planets. And this whole thing started somewhere around 1995. We could argue about that, but the very first planet was discovered then orbiting a normal star, what's called a main sequence star. And Time magazine got it right. The reason that anyone was interested in the detection of a planet is because it gave new life to this question: is anybody out there? Are we alone? Okay. How the discovery of 2 planets brings us closer to solving the most profound mystery in the cosmos. And I'll just say that, right before 1995, around 1993, I think, there was a meeting, much like there's a meeting going on right here, that was going on right here today. And astronomers at this meeting were talking and saying, people have been looking for planets for a long time, and they were not finding anything. So what's the deal? And now it seems like kind of a funny question, but there was real discussion about maybe there aren't any other planets around other stars. Maybe we're it. And that's an incredible, to look back. 1993, right? It's 20 years ago. 20 years ago, we had no idea. And I like this analogy because right now we say the same thing about, is there life out there? Well, why haven't we found it? We've been looking for a long time, right? And so, there's an analogy here. Okay, so the team that I started working with was Professor Steve Vogt at UC Santa Cruz, who was actually my professor when I was there. Jeff Marcy, who's a professor at UC Berkeley. Paul Butler, who's now at the Carnegie Institution of Washington. And then me and National Geographic had this very artful layout of Steve standing here with his mirror. He's an instrument builder. Jeff and Paul are looking through an iodine cell. And I'm catching stars and looking for planets in my hand, I think. But it was a kind of nice idea. So in 1995, first planet found. Then, the planets came slowly in those days. Every planet was like a press release, and the limousines would whisk people in, and there would be news documentaries, and they would have you walk up and look at the telescope and do all of these crazy things. In 1997, the exoplanet searches finally had enough credentials. We had enough credit, okay, that we were able to get telescope time at the Keck Observatory. And so here, of course, are the mighty twin Keck telescopes on the neighboring island. Ah, too bad. This is one that's not going to work. Okay, so in this frame. So the technique that we're using, that we've been using since 1995 to find planets, is called the Doppler technique. And when I look at a star with a telescope, I see not a little, white dot like you might expect, but the white dot goes through an instrument, a spectrograph, spreads the light out into a rainbow of light, and then in that rainbow of light, there are these dark missing lines, okay, that come from atoms and molecules in the atmosphere of the star. And first of all, just figuring out what those lines are tells us what the star is made out of. So that's pretty interesting, and people have been doing that for 100 years. But then also, if the star is moving because of something called the Doppler effect, those spectral lines coming from the atmosphere of the star, will shift. They shift to the red if the star is moving away from you, to the blue if the star is moving towards you. So now, if there is a planet that's orbiting a star, it's actually tugging the star around a common center of mass. So the star wobbles as well. And so what you would see is the star coming towards you, going away from you. So you'd see these spectral lines, red shifted, blue shifted, red shifted, blue shifted, in a periodic way, with a periodicity that was the same as the orbital period of the planet. Okay, so that's how the technique works. Now, if I were a theoretician, I would make a plot like this. Even I'm not a theoretician, I still made that plot, showing the speed of the star in meters per second. So, a meter per second, that's about that speed. And then time in years. Okay, so what you see on this plot is this blue wobble that you would see if we lived on a planet orbiting another star and we were looking back at the sun. We would see the sun wobbling around with a 12-year period. So if you look at the x-axis, one complete cycle is about 12 years, because Jupiter takes about 12 years to complete one orbit. Jupiter's the most massive planet in our solar system. It tugs the sun around. Then if we look for 30 years, we would see that this cycle was modulated by a second cycle from Saturn, which tugs on the sun, okay, with a force that amounts to a velocity of only 2.7 meters per second, because Saturn is further away. Okay, and an orbital period of about 30 years. So I have no idea what's going to come up here. Ah, yes. But I'm not a theorist, I'm an observer. Whenever I go and I take a measurement, there's some uncertainty. I can't nail it precisely. And these error bars could reflect the measurement precision of the technique. They certainly did reflect. We're doing a little bit better now. But you can see that, if you had this data set, first of all, I'd be observing for 70 years, right? And it would still be pretty hard to actually detect Saturn. So this technique allows you to find big planets. The more mass the planet has, the larger the velocity that it induces. If I were to put the wobble that the Earth induces on the sun, you wouldn't even see it on this plot, on the scale of this plot, because it's only 10 centimeters per second. Okay, 10 centimeters per second over a year. So 6 months, 10 centimeters a second that way, right? And then the other 6 months back again. So pretty tiny. And that's what makes it hard to find other planets like our own. Okay, but nevertheless, we think it's an important goal. Astronomers have a process called the Decadal survey. Every 10 years, we sit down and we put together a panel of, the most august astronomers in the field who say, what have we found in the last 10 years? What are the priorities of the field? What are we going to do in the next 10 years? We realize that to a lot of people, astronomy is a hobby, right? That there are a lot of priorities that this country has. Education, right? Social programs, defense, all sorts of things. And so I think we're very careful about keeping things in order and making sure that we're all moving together. So it's pretty cool. And the Decadal survey said this time, wow, looking back, we have found so many exoplanets. We think this is a priority. Hundreds of planets have been found. We think the priority for the next decade should be the detection of true Earth-like planets. So planets that could harbor life, planets that are at the right distance from their star that they might have oceans of water. So far, this technique that I use, called the Doppler technique or the radial velocity technique, has found over 700 planets, okay, orbiting nearby stars. So it's been quite successful. JD, when he introduced me, he told you that I started working in 1997 on exoplanet detections. So I think that's a good time to start this plot. Scientists are always looking for correlations between data, okay? And so what you're going to see in the subsequent plots is, oh shoot, I hope it works, is that, you know, the years will tick by and you'll see new planets appearing. So when I started, actually 3 of these I discovered in 1997. There had been a few planets that had been detected. So the correlation again, if this works, yes. I start in 1997. All of a sudden, we find lots of planets. It's clearly the Debra Fischer effect. But for some reason, my colleagues haven't picked up on this. So here we are. This actually punches through the roof up to almost 100 detections, okay, in last year, 2011. And the interesting thing is that the kinds of planets that are easiest to detect are the big ones, right? These are planet mass, sorry, it should say in Jupiters, okay? So there's something about nature. Nature doesn't make planets that are 10 times the mass of Jupiter very often. Instead, nature prefers to make planets that are smaller than Jupiter, sort of super Earth or Neptune-like planets. So it's kind of like, right, the typical, if you looked at the typical birth weight of human babies, you know, most of them are around 5 to 7 pounds. It's very rare that you're going to see a 25-pound baby, right? Hopefully. So the same thing. There's something about the mass and the environmental conditions in the protoplanetary disk where planets form or are born that sets this interesting limit, something we just didn't know about before. Okay, so again, 1997, when I would go and give science talks, about half of the astronomers, at least, would be openly, I wouldn't say hostile, but they were certainly skeptical. Okay, great, you're showing us your data, that's fabulous, but we don't agree with your interpretation. How could you possibly get a planet like Jupiter in a 4-day orbit, right, which is what the first planets were like? That just doesn't make any sense. So instead, they thought we were seeing pulsations in the star or something else. But we knew that given enough detections, we would have an orientation, right? The planets can be, if you imagine the orbit of the planet is like a hula hoop around my head, which is the star, then that hula hoop can be, you know, tilted so that it's exactly edge on to our line of sight. It's not going to happen very often, but if for the planets that are close in, it'll happen about 10% of the time. So we knew that after we had found about 10 of these so-called hot Jupiters, hot because they're close to the stars, that one of them was going to be seen going across the face of its star. And as you guys know who measure photometry, when that happens, the starlight dims, and that dimming lasts for about 3 hours. And so we would tell our friends who measure the brightness of stars, okay, look at this star. And if it's going to transit, we can tell you that it'll happen at exactly 8:27 tonight. Okay, but we don't know if the orientation of the orbit is going to be just right. So one night in 1999, Greg Henry at Tennessee State looked at 5 stars. Okay, 4 of them were controls, and then the 5th one was HD 209458, which was our star with a planet. And at exactly, well, within 30 minutes of the predicted time, the starlight dimmed as the planet cast a shadow going across the face of the star. So at that point, the scientists, I would say all except a very few people, then said, okay, that's compelling evidence. We have 2 lines of reasoning, right, which both support this idea, and there were other things that we were looking at as well. So they accepted this notion that that what we were seeing in our radial velocity data really were planets. So even in our own solar system, of course, the planets will transit. Mercury transits more commonly. Hopefully you're all going to be able to see the transit of Venus tomorrow. I think first contact is at 11:10 p.m. tomorrow afternoon. Just as a caution, don't look at the sun directly. You have to have special glasses or special protection to do it, so be careful. But I know that the astronomers here are setting up places where you can view the transit of Venus. This is a rare event, okay? The next one will be in, oh gosh, you guys help me, is it 2117? Okay, yay. All right, exactly. So I don't think I'll be around then, so I'm going to try and see this one. Okay, another movie that doesn't work. All right, so anyway, as I said, what you would see if this animation were working is a little planet crossing the face of the star. The brightness of the star dips down. Now, you can imagine if it's a really tiny planet, that dip is going to be small. If it's a big planet, then it dims a lot, right? And so what we detect is really the cross-sectional area. Ooh, that's what I should have done if it's a big planet. Then we detect the ratio of the radius of the planet to the radius of the star, or the cross-sectional areas of those two things, with the transit techniques. I know a lot of things that aren't going to work. Too bad. Okay, so from the ground, and I don't know why this line is here, the transit technique has detected almost 200 planets. This won't work either, but in March of 2009, the Kepler mission launched, and the Kepler mission is just, all of us who spent 80 nights a year at the telescope, painstakingly, measuring the velocities of stars, have watched in the last 3 years as this incredible watershed of transiting planets has come out of the Kepler mission. It's fantastic. There's something like 2,300 planet candidates now, transiting planet candidates. And Kepler is just rewriting the books. And because of the sensitivity, the measurements from space, they're detecting these tiny, Earth-like planets, Earth-sized planets, I should say. Okay, I know. All right. Have to get fancy. All right, let's see. Well, I wanted to highlight a few of the things that I find especially cool about the Kepler, some of the Kepler detections. These are just anecdotal, but cover of Nature magazine, just in the last year. Here's a system, okay, where the star, around the star, there are 6 planets, and they're all transiting. Sometimes, 2 will transit at the same time. You'll see them you'll see a strange shape to the transit curve. So that's amazing. And Kepler has discovered a couple hundred systems where the planets where there are multiple planets. So this is a new theme, okay? We had seen a hint of this with the Doppler data, the radial velocity data, that multiple planet systems were common, right? In our solar system, 8 planets. So now we're seeing that this is what nature does, okay? Nature makes planetary systems with lots of planets. You could have guessed that, but now we know. I love this system, Tatooine, which was announced last September. Here you see a sun-like star, actually a little bit hotter and larger than the sun, and an M-dwarf, a cool M-dwarf star. And then these 2 stars orbit each other, and then around these 2 stars, there's a planet, which transits in front of them. Okay, so it was named Tatooine because if you've seen Star Wars, you know that Luke Skywalker starts out on this planet Tatooine where there are 2 stars in the sky. So it's a Saturn mass planet orbiting a double star system. That's amazing. And it tells you, wow, planet formation is incredibly robust. Okay, this is another slide that isn't working, but this is the Kepler orrery. So Dan Fabricki at UC Santa Cruz has put this together, and normally all the planets will be spinning around, and you'll see them going. But these are just some of the multiple planet systems that the Kepler mission has detected. And planet candidate count now up to about 2,700 planets. All right. Now, if you want to join in the search, we have started a project. So myself at Yale, Chris Lintott at Oxford University, Kevin Shawinski, who's an Einstein Fellow at Yale, and Meg Schwam, who's an NSF Fellow at Yale, and two of my students, John Brewer and Matt Jaguar, put together a website. It's like there's a website called Galaxy Zoo where you can go in and you can you're asked to identify images and say, does this look like a spiral galaxy, or and the power of the people going through and doing this is absolutely incredible. So as soon as I saw the Kepler data, I realized, wow, this is perfect for the citizen scientists, because John Jenkins, who's one of the Kepler scientists that's at this meeting, I could see everybody struggling, all the scientists struggling to try and, there's a fire hose of data. Try and understand the data and look at it. And I knew that this is something that anybody, could look at and figure out as well as the scientists. And indeed, the citizen scientists have found planets. We've published already 3 papers with new planet detections, and the people who are the first identifiers are co-authors on the papers, and we have 2 more papers in the works. So one of them, which is since you don't know the name, it's okay I think if I tell you, but one of them is a planet going around a binary star system again, like Tatooine. And in fact, as soon as Tatooine was discovered, I looked back and realized that the planet hunters had found it. Meg had come to me and said, hey, what do you think? And I said, nah, it's just too unlikely. And I was too busy and didn't follow up, unfortunately. But they had found that one as well. So this is a site, planethunters.org, where you can go and log in. It's real quick to learn how to look at the light curves. You're asked 3 quick questions. The people who did this are now something like 40 or 50,000 people, the public, who use this site. They've contributed the equivalent of one person sitting down 24/7. You never take a break, classifying light curves. You never get tired for 200 years, 200 years. So however dedicated the scientists are, we can't do that, all right? And so this network has been incredibly powerful. And we're starting to put together new ways that people can tap in and tell us about stellar variability and things like that, in addition to planets. So so it's a small number compared to Kepler, but come on, it's so cool that the people and the public were able to participate. Then there, of course, are detection techniques where you could take a direct image. You could see the planets orbiting in this particular system. There's a planet B, C, D, and E has been found now. So this is an amazing system. All right, and that's a great way, right? That's what people really want, is just show me the planet sitting there next to it, and then I want to see if there's clouds on it, right, and the pale blue dots. And so that's where we definitely want to go, but I think we still have a ways before we can get down to finding Earth-like planets. So I, in a longer amount of time than I meant to, told you about all these different observational techniques. Of these different techniques, microlensing, transits, Doppler observations, imaging, how many of these techniques are going to find Earths, where I really do mean an Earth, that could support life, and how are we going to find many of them? Well, the Kepler mission is actually already, I think, doing this. However, these stars that the Kepler mission looks at are typically very far away. And we want to follow up on these stars, so we want them to be close. So here comes Project Longshot. I'll tell you about this technique that I'm trying. I now have an instrument lab, and we're trying to build brand new instruments that are going to really push down the precision so that we can measure these 10 centimeter per second motions. It's almost impossible, but we're still going to try it anyway. Impossible because in your CCD camera, there's a silicon substrate. You guys who use CCDs know about them, right? We're talking about measuring the shifts of spectral lines that are 2 or 3 pixels wide across 10 silicon atoms, back and forth, over 1 year. But we're already doing this to 100 silicon atoms. So we just have to do whatever we've been doing and do it 110 times better or something like that. Okay, so I love this plot because one of my dear friends, Greg Laughlin, who's a professor at UC Santa Cruz, is a theorist, and he has a great blog, oclo.org. Fantastic. It's beautiful, lots of incredible information. But I remember him posting this plot and saying, okay, look, if we look at the year of discovery, here's 1995, here's the Debra Fischer effect, right, kicking in, 1997. All right, then if you look at the mass of the planet that's detected over time, we're doing better and better, okay? And if you just wait 3 more years, you'll get down to an Earth, right? But, okay, in fact, with each one of these improvements, there was a significant improvement in the engineering of the instrument or in the software analysis or something else. So, yes, we're doing better, but taking the next step is going to be tough, okay? And so that's what we're working on. We know what the obstacles are. The instruments aren't stable enough. We have errors when we do our analysis. The signal-to-noise ratio, the number of photons we get isn't good. And then the stars themselves are causing problems. If you think about our sun, it has these flows, right? Explosions, flares, coronal ejections, motions of 100 meters a second, kilometers per second. All right, and so it's not like we're trying to measure, and we're trying to measure this thing that's boiling, right, at 100 meters a second to 10 centimeters a second, the whole body. Okay, so that's hard too. All right, but that's okay. Okay, so one of my students, this didn't copy very well, helped to figure out whether or not the information content was there in the spectrum. We've run simulations that show that when we get to high enough signal to noise, we can get down to 5 or 10 centimeters a second. Okay, but we have to control the systematics of our instruments, and then we're going to have to look for signs of motions from the star in the atmosphere itself. Yeah, this is just a picture showing what I said before, that you've got some spectral line, right? 1 pixel is 15 microns typically, and 1 meter per second, which is what we're doing already, is a shift in this line of 1/1000th of a pixel. Okay, so we're doing that. We just have to get down to something like 1/10,000th, 1/20,000th, whatever. Okay. So instrumental stability is, I think, a serious issue. Let me just go back here, right? This is when I went to CTIO, I said, Greg Laughlin, in fact, and I got together and said, you know, the perfect system is Alpha Centauri. Those stars are killer bright. They're 0th magnitude stars. It's a binary system. Talked about that, not exactly edge on, but that means you get the full wobble of the star. The stars are metal rich. They're a little older than the sun. They're close, and even if we have 3 meter per second error bars, big error bars, if we just take 90,000 observations, we should be able to get down to really low mass planets. So we found a telescope at CTIO in Chile that was just about to be shut down. It didn't have a spectrograph, so we looked through the basement and found this old thing. And I got $80,000 from the NSF to refurbish it and put it back on the telescope. You can see, it's always a bad sign when you get the duct tape out, right? Probably not a good sign for stability. And we took our data in the first year, and we measured the velocity. This is Alpha Cent A, of course, has a B companion. And so what you see here is the orbital motion. And then if there were a planet, then it would be wobbling about that. This is just scatter in the data. These are errors, systematic errors. So there's no planet, no sign of a planet there. And our precision ended up being something like 5 meters a second, which was not good enough. So we went to the NSF in 2009 and got funding to build a new spectrograph, which we've done. Here's Andrei Tokovinin, Chris Schwab, who's a postdoc of mine at this meeting, Julian Spunk. Lauren just built the telescope. In fact, on Saturday night, we just locked everything up, and we're just ready to go now. We've done everything with this spectrograph that we know how to do in terms of stability. Now we'll find the next problem, but that's okay. We've pushed this as hard as we can. So I'm pretty excited. We took some test data, and our test data are really good. They have individual error bars of 30 centimeters per second, but that always underestimates the systematic errors. But even the systematic errors look like we're better than a meter per second. And we just grades, which is what we just completed. Maybe the next time I come, I can talk to you and tell you whether or not there are planets 1 billion years. Yay, his thumb is up. I know that's a good sign. Screwdriver.
Which I realized I did not need.
Okay, thanks. All right. Okay, so anyway, what does make an Earth planet or a planet sort of Earth-like or habitable? Well, I think it has to have about the right mass, right? It has to have a mass. If it's too small, if it's like Mars, it won't hang on to its atmosphere. It doesn't have enough gravitational pull. And if it's too massive, there could be other problems. The planet could grab on quickly to a lot of gas in the disk and become something like Uranus or Neptune or Jupiter or Saturn in our solar system. But if it's something like somewhere between maybe 3/4, a Venus-like planet, up to, we don't know what the upper limit is. Maybe it's 5 Earth masses. Maybe it's 10. That might be pushing it. Then it's a world that, at least for life as we know it, it might be a hospitable place with plate tectonics that communicate with the atmosphere. The planet has to be at about the right distance from the star. You guys know the Goldilocks story. If it's too close, it's too hot, the water evaporates away. If it's too far from the star, the water's frozen over into ice. So it's got to be at just the right distance from the star so that the planet has liquid water on its surface. Biologists tell us that's really important for water as a solvent for life, the evolution of life. And the planet needs to be in a fairly circular orbit, right? If it's in a very eccentric orbit, then it spends a lot of time out here where it's cold and then comes diving in around the sun, and the temperature swings can be hundreds or 1,000 degrees. Okay, so it's bad enough here, just summer and winter. Well, not here, right? But, on other places on this earth besides paradise, it's hard enough to survive just with changes of, 40, 50 degrees, 1,000 degrees. That would be unimaginable. Okay, and then finally, yes, I don't know why this one is here. Actually, I'm going to skip it. I'm sorry. The combination of I got to go back now. All right, this doesn't actually really fit here, but all right. The one point I wanted to make, this should have been with the transiting planets, I guess, is that here we're able to look at these planets that cross in front of their host stars. We're able to figure out their mass from the Doppler measurements, their size from the dimming, okay, and therefore we come up with a mean density for the planet. And we sort of understand the physics of materials, and so we can start at different guesses for what the core mass is. But then if you do play a sim planet game where you build it up, you've got to end up with something that's the right mass and the right size, okay? And so you're distributing this density of material throughout the planet. And with these techniques, we're able to take systems like HG 149026, which was one that I discovered at Keck. And actually, it sounds crazy, but this planet orbits a star that's 200 light years away. Okay, you couldn't see the star with the naked eye. You need a telescope. You can't see the planet even with a telescope. And yet we're able to sit here and say, look, I know that the interior structure has 70 Earth masses in the core, plus or minus 20, and what the size is. And as the planet comes around and the atmosphere is illuminated by the starlight, we can see some of the constituents of the atmosphere of the planet, even though we can't see the planet itself. And we can compare it to Jupiter. And we have, that's amazing. A planet we can't see, orbiting a star hundreds of light years away, that we're able to make these deductions. And by we, I mean the astronomical community, the theorists and so forth. This is an image. This is where we're going. It will happen in the next decade. You guys will be hearing more about this story. As we find more planets that transit, and we take a spectrum of the lit up atmosphere of the planet, we can see the composition. And here, these are very crude. You would hardly call it a spectrum, right? I mean, the blue and the yellow lines are theoretical spectra. The data points, this is very crude. These are just sort of photometry, infrared bands from Spitzer. But you can constrain the types of atmospheres and the type of planet that you have. So we're going to be able to see atmospheres of Earth-like planets. And that's important because if you looked at our planet, do anyone know what would be totally weird about this planet? The atmosphere of this planet, to be specific? The oxygen. Well, ozone, right, which is, yeah, the same thing, oxygen, O3 instead of O2, exactly. Okay, so if all life on this planet died, it was extinguished, okay, in something like 10,000 years, the oxygen disappears. Okay, the oxygen is only here because there's life on this planet. So we want to look at the atmospheres of other planets and see if we see the same kind of what we would call disequilibrium chemistry in the atmosphere of the planet. All right, so now how does our solar system stack up? Okay, it's been 17 years. We knew what our planet solar system was like. How does it compare to other solar systems? Well, we always had a model for planet formation. It's evolved quite a bit. But one of the neatest things to me is that now we found other solar systems, many but not all, are coplanar. The multiple planet systems are coplanar, like the planets in our solar system are in a disk, a flat disk. We find signs of these planets forming in protoplanetary disks. But one of the neatest things is that, remember this first system I told you, it's a Jupiter, it's in a 4-day orbit, and astronomers said, we're going to believe that that's really a planet, right? The early interpretation. Well, it was a planet, it is a planet, but it formed further away from the star and then migrated inward. And so one of the questions we were all asking ourselves is, if so many of these gas giant planets migrate inward, why didn't that happen with our solar system? Why is it that, Jupiter and Saturn formed further out, they stayed out there? And now the answer, we think, is that the planets in our solar system have moved around a lot. And the way we know that is by looking at the Kuiper Belt objects. So the Kavli Prize was just awarded to Dave Hewitt and Jane Liu and Mike Brown for their work on the Kuiper Belt objects. So it's the same thing in my house where maybe I don't clean as well as I should, right? And there are dust bunnies all over the floor. And now I have a puppy who's 5 months old, and he goes tearing under my bed. And if I look under my bed, I can see, this sort of U-shaped pattern where he went in and came out again. And so I know what he did just by looking at the dust under my bed, right? And it's the same thing in our solar system. The Kuiper Belt objects are the dust bunnies. Okay, and the planets, Jupiter and Saturn and Uranus and Neptune, have blown them around into a distribution, a pattern, which suggests that Neptune and Uranus actually formed in between Saturn and Jupiter, and that Jupiter, there was a sort of a grand tack, as one of the theorists called it. Jupiter moved inward almost to the point where Mars is, and then moved back outward. Now, how all that motion happened and we still end up on nearly circular orbits is kind of a puzzle to me. But it's one of the things, the Jupiter's do-si-do, as some people call it. But it's something our solar system has in common with other exoplanets. This is something, looking at the Kuiper Belt, understanding our solar system in the 1980s, some astronomers at Caltech said, the planets in our solar system must have migrated around. And everyone said, yeah, go back to, put that one in your filing cabinet. And now they can pull it out and say, this makes sense because of what we've seen elsewhere. So how do we compare? Well, our architectures, there are multiple planets in our solar system, multiple planets in other solar systems. Our planets, we know better how they formed, that they moved around, and that's definitely true of other worlds as well. It's true that about 1% of other stars have these Jupiters that migrated in. We call them hot Jupiters because they have orbits of just a few days. But those stars tend to be very metal rich, lots of iron and silicon and titanium in them. We know that they're in multiple planet systems about 30% of the time. And we know now from Kepler that planets like our Earth occur around some 30% of the stars. Okay, that's a lower limit. All right, it's got to be higher than that. And that most of these systems are multiple system. So we're putting together a really interesting picture of how our solar system compares. So we are different, to come back to the original question, we are different from these other solar systems, but there are some characteristics that are in common. This whole process of planet formation is a chaotic process, all right? It's a wild and violent and crazy process, and so you end up with a whole bunch of, sort of roll of the dice, whole bunch of different configurations. Anything, it's gravity. Anything that's gravitationally stable will survive. Okay, so I want to end on what I think is a high note, the idea that astronomy is really kind of a vision plan for the human race. If you have a business, you know that you have to take care of a lot of day-to-day things, right? But if you want to be a Steve Jobs or a Bill Gates, right, you want to be really great and successful, you also have to have a big picture of how things go. And one of the, how much bigger can it get than this? Figuring out whether or not there's life somewhere else in the universe, in the galaxy. And so, Frank Drake penned this famous equation. It's not really an equation, it's just a sort of a probability, trying to distill our knowledge. How many communicating civilizations might there be? Well, it depends on how many stars there are, what fraction of those stars have planets, what fraction of the planets are Earths, what fraction of those planets, Earth-like planets, does life develop. Even if life develops, they could be, dinosaurs or dolphins and not communicating. And so what fraction of the planets then does life become technological? And then finally, what's the lifetime of communicating civilizations? We've only been here for how many seconds on the cosmic calendar, right? If we make it like the dinosaurs did for 6 days, just think what we can do. It's incredible. So Frank Drake, his license plate basically says N equals L. He thinks that all these other things, I've highlighted these things where we can cross them off now. We know them. We didn't know them all before. Now we're just working down the list to try and better understand those other terms. His bet is that, it all comes down to what is the lifetime of the communicating civilizations. These discoveries that we've made have percolated down to pop culture. So we found early on a rock band, 51 Peg. Should all go buy their CD. World Pop for the World, 47 UMA system. So, it's cool that these are results that mean something to a lot of people in some ways, that they incorporate them into their lives. But back to this cosmic calendar, this idea that yes, we've only been here for seconds in the last, half of a minute of the cosmic year. Yes, we're on this tiny little dust mote of a planet, just one of billions, trillions of stars and planets that orbit them. But we are spectacular as a species, right? Think about it. In the history, we're able to look back and figure out who's been here before. We're able to put up a plot that says life started in September on the cosmic calendar. We're able to look out and figure out that the universe started with a big bang, right? I mean, the dinosaurs were just munching along for 7 cosmic days. They had no idea that a near-Earth asteroid was going to come in and wipe them out. But we have people, who are watching, who are protecting us, who are taking the long view. We're trying to figure out what's going to happen to the evolution. We figured out how stars work, right? And that our sun is evolving. Our oceans are going to evaporate away unless we do something about it. Yes, we have a lot of challenges, and there are a lot of scary things about humanity as well, right? But I think we're remarkable to have the audacity, the courage, the intelligence, the vision, to reach beyond ourselves, to build these monuments to humankind's curiosity, the observatories on mountaintops like Mauna Kea or Haleakala, right? We're the first species that realizes, our origins, our history, and can sort of get a feeling for our fate, for what's going to happen. And we're the first to be able to think about this. Okay, we're in trouble now, right? There's climate change that's happening, and it's induced by humans. but we're thinking about engineering solutions to this, how we're going to overcome them. So yes, there will be Ebola viruses, and there'll be all sorts of bad things that happen, you know, but we are amazing because we can stand up and see and understand and confront these things. So I'm going to end on that note, and thank you so much for coming out tonight. Yes. Okay.
When you ask questions by the audience, please repeat them so people
Okay.
listening in the
Okay.
virtual world
Yes.
can hear.
Questions?
So tomorrow Venus will transit the sun.
Yes.
What percentage of the sun's light?
Oh man, you guys know this much better but you did see the picture. So the question is, tomorrow Venus will transit the sun, and what fraction of the sunlight will be occulted? Because we're so close to the sun and Venus, we benefit from this foreshortening. But you saw the picture. There was Mercury on the one side and Venus on the other side. It's a tiny dot. And so if you were measuring the photometry, I'm not sure, some of you guys might know better than I do what the dip in the brightness would be. Instead, what you'll see is the dot moving across. I would guess something, yeah, less than that. Yeah. Yeah. Good, yeah, good question. Yes? That's right. Oh man, that's a long question. There's a great book though. It's called The Transit of Venus, where the author discusses this whole idea that by measuring the transit time of Venus, people were able to figure out the distance between the sun and Venus and the sun and the Earth. Yeah, but
Captain Cook has something to do with that.
yeah?
Yeah.
Okay.
NPR said they talked about the triangulation that happened in the 70s.
Right. So it's geometry, right, that's been used. And the question was, how do they use the transit of Venus to figure out the size of the solar system? Yes.
Two questions.
Yes, two questions.
One, I just want to challenge that.
Okay. You could challenge that we're incredible?
I won't challenge that we're incredible, but I will challenge that pre-existing organisms could have had philosophy. The fact that they don't have the dexterity to create artifacts does not mean they didn't look at the star and contemplate the universe.
Okay, but do you think they actually had archaeological digs and that they figured out there were species before? Okay.
There are many differences we can argue about.
Okay.
I just want to talk about end-on, sort of side-on planetary systems. At the moment, all I'm hearing is that you're sort of looking for a snapshot and you see the planets and you see the moon. Is there any move to use jitter or something like that, or is that so? I suppose it's so indetectable.
Okay, so are we talking about the transit technique or the velocity technique? Transit technique, okay.
They're both Dopplers going forward.
Yeah, in both cases you want to have systems that are close to being edge-on, and if they are face-on orbits, for Doppler you won't measure any radial velocity.
Absolutely. Is
Yes.
there anything you can do with those? I was thinking jitter, but then thinking about it, the jitter's going to be minute. So
Yeah, I think we haven't, because there are hundreds of systems, we haven't been pushed in that direction of being so desperate to try and dig down. Yeah.
I'll try and come up with something.
There are some people who say that close-in planets will stir up the star in ways that increase the activity, the chromospheric activity. So far, I have not been convinced that those explanations are correct. But you had two questions. Did you? Oh, the first one was that's right. We are incredible.
There were several others. but
Okay.
those are-
Okay. Yes.
I was wondering, is there any moons that we know of exoplanets? Is there any
Moons of exoplanets. Has anyone detected moons of exoplanets? That is a great question. There's a postdoc at Harvard University, kid to me, who's actually looking, David Kipping, who's actually looking for exomoons in the Kepler transit data. So he hasn't found them yet, but people are interested. One of my undergrad students at Yale did a project last semester where he tried to figure out how a Jupiter that's migrating in might capture them and then sit like Pandora, right, in the habitable zone with a moon. So it's almost certainly they have them, and it's just been too difficult to detect them so far. Yep, good question. All right, yep.
There was that, this is kind of a two-pronged question.
Two-pronged question.
You said 30% have possible planets that are
Earth-like planet. Yeah,
Is that 30% of stars with planets or 30% of stars?
30%. The Kepler mission says that something like 30% of the stars that they're looking at have planets that are low in mass, probably rocky Earth. They may be Earth, super Earths, something like that. That confirms what we're finding with the Doppler techniques too, or it's the same result we're seeing. So I suspect that number is more like 50% or 80%. Yeah.
In the galaxy.
In the galaxy, right. And what's interesting is that we're looking at, with our technique, we're looking at very nearby stars. The Kepler mission is looking at stars that are a little bit further away. So even, you know, sort of sampling two different parts of the galaxy, we're seeing the same result. Yeah.
So
yeah.
sorry.
No, go ahead.
So the way near the beginning, you were talking about the every 10 years, the symposium, whatever.
Right, the decadal survey. Yep.
Yeah, decadal survey. And one thing they said was something about we have found with startling diversity.
Right.
Startling diversity. Like, what? Was that just what you were talking about?
What made them diverse?
How
right.
much diversity can you see?
Right. So the decadal survey is saying, you know, they reflected back that in the last decade we found, you know, hundreds of planets with startling diversity. The diversity that they were talking about was the range of eccentricities in the orbits, the range of core masses. Sometimes we see Jupiter-like planets that are inflated. We don't know why. Sometimes they're smaller and denser with the same mass. So that's what they're talking about. Yeah. Yes?
Can you simplistically give us an idea of what causes planetary migration?
Sure. Simplistically, can I give an idea, sketch out an idea of what happens with migration? There are two dominant theories, and I think probably both of them work. I mean, both of them may actually, you know, operate. The first is that the planets form in disks. If you remember that picture that I had of the disk and the planet forming in it, and as it builds up mass, it clears a gap. So I think of the planet rolling around like a snowball, right, collecting stuff and clearing out this gap. And now material is still streaming in towards the star. All the material in the star feels the gravitational pull of the star at the center of the disk. So it's streaming inward, and if it builds up enough mass on the outer part of the disk, it'll exert a torque on this new formed planet that drives the planet in. If the mass is on the inner part of the disk, it drives the planet out. Okay, so there's just the mass of the disk that can cause the planet just, you know, sort of brute force, you know, muscle it inward. But then planets aren't forming in isolation. There are many planets that are forming, and they're colliding with each other. And so there's planet-planet scattering that's almost certainly occurring as well. And in that case, one guy goes in, and the other guy carries the angular momentum away and ends up going outward. So, yes? Okay, is it possible to detect planets orbiting black holes? So we can detect stars orbiting black holes because they're accelerating and they give off a lot of light. But not yet for any planets. But you might speculate that those stars have planets, right? And they're also going around and falling down the drain of the black hole as well. Yeah, if they're far enough away from the black hole, as long as they're not inside of this Schwarzschild radius, then they could be stable for some time. But the black holes that we know about, like at the center of our Milky Way galaxy, are so far away, we're not even looking at those stars for exoplanet searches. Good question. Yes?
I'm completely ignorant of everything you've gone through tonight, but
Okay.
the last paragraph of the research
Yes?
intrigued me because I would like to know how you consider dialoguing the engineering solutions.
How we're going to what?
Dialogue. How are you going to have interaction between the solutions, the engineering solutions? How is this going to come about? How are you going to have dialogue between the different views?
Oh, you mean, okay, so let's take the issue of global warming as one threat, right? And so your question is, how do we talk to other countries, or who are we dialoguing?
Ourselves. How do we have a discussion
Yeah.
that he'd be able to ask you some questions about some of this stuff.
Right. So, okay, so I'm a little bit cynical. There are a lot of countries, France, for example, you know, that say, we just roll back, we become an agricultural society again, we put aside our laptops. I say, and sorry, in the U.S. that is just not realistic. That is not going to happen. Nor will we be listening to France if we decide that the problem gets bad enough. Okay, that's my cynical view. This is not politics, right? But I think what might happen is that, yeah, either we come together and work as a collective world, right, which hasn't worked out so well so far.
Why do we do it?
Or like a UN kind of thing, or there will be rogue nations that consider themselves to be in the know, powerful, with the wherewithal, and they will simply do stuff. Like you can imagine, one suggestion is put particles, reflective particles, up into the Earth's atmosphere, and then the sunlight that comes in, some fraction will be reflected away, right? So a country could do that, and everyone else might disapprove, but if they, you know, if it happens, then...
Well, the dialogue that went on in England a couple of years ago didn't really work out, and they started really questioning and asking them for their information that
Right.
they base their conclusions on. So it would appear to me that it's very difficult to get...
It's very difficult.
Even an environment where you can get enough...
Right, but that's because you're sitting here in 2012. If we come back in 40 years, all right, and the projected models are what the MIT scientists and other people say that they'll be, then nobody will be disputing whether or not there's a problem. We'll just be trying to figure a way out. So, yeah. So I think it's just not bad enough yet. Yes?
Has anybody thought about the December before that January in the beginning there?
Oh, absolutely, absolutely. And, you know, it's a realm for theorists, creative theorists. I'm very empirical. I mean, to me, science is, you have to have testable hypotheses, right? If it's not testable, it's not science. So it can be, there's this huge, you know, fantasy and creative ideas about what happened before. Maybe before we had better measurements, right, that the universe is actually accelerating in its expansion. People had the idea that, you know, maybe it would actually collapse again. There'd be a big bang and then a big crunch again. So there are a lot of ideas, but it's hard, impossible right now to get data. Okay, maybe someone will think of something. Yeah.
Is the Kepler mission seeing the proportion of transiting stars with transiting planets that it's supposed to?
Right. Is the Kepler mission seeing the fraction?
And are we sure that every star might have bodies that transit?
Right.
But
Okay.
we just don't always see them.
Right. So the question was, is the transit mission seeing the number or fraction of transiting planets that it was supposed to? The Kepler mission was launched because we had no idea what that fraction was going to be, right? And we didn't want to build a space mission that would cost $10 billion to go up and look at stars if we didn't have a sense of the statistics. So the things we're learning from Kepler are brand new. And the answer could have been anything. And so they correct to get that 30%. Yes, we're saying what's the fraction that are edge on. We're assuming that there's a random orientation of the orbits, and we're making that correction factor.
So is it, are we getting a feel for what that fraction should have been? How many stars have planets?
Yeah. In the last several billion years, most stars that formed should have formed with protoplanetary disks and planets. In other words, I think you would have to have had something catastrophic happen that got rid of the disk. And one thing that could happen is stars form in clusters. So if your neighbor happens to be a very massive star, its lifetime is 10 million years. I mean, it goes through the whole thing and then it goes supernova, while you're just still collecting the planetary, protoplanetary disk, and it blows away your whole protoplanet. But that's going to be a very rare event. Massive stars are extremely rare, right? So the very first stars that formed after the Big Bang were comprised of hydrogen and helium only. All right. If there were exotic hydrogen planets, there was no water, right? There was no veneer of prebiotic chemistry. there was, nothing, for evolutionary purposes, nothing. So, but somewhere along the line, materials were manufactured in the cores of stars, and then planets and life formed. So I think most stars, to answer your question, I would think, I don't know if it's, I'm going to say 75% plus or minus 25%.
Stars themselves tend to form in, multiple bodies.
Yeah.
Stars are binary or more.
Yeah, something like half of the stars are in binary systems, exactly. But, Alpha Centauri, A and B, binary system. We are finding lots of planets that orbit one star, the other star, or both stars. Yes?
I've got a question. So, is our goal to inhabit an exoplanet?
Okay. Is our goal to inhabit an exoplanet?
Or to
First question.
discover that there is life out there in case we become extinct?
Or to what?
Or to just to take comfort that there is
To
life
take
out
comfort
there
that there's life somewhere else because we might. Okay.
I
That's the answer to that question. To your question is going to have to be defined by the future generations of humanity. My guess is that, honestly, the trajectory that I see, if you guys have heard of the singularity, is that we are merging more and more with technology. And my daughters are humanists, and they hate it when I talk about this. But it's true, right? There are prosthetic devices that we have now that allow us to hear, allow us to see, implants in our brains eventually. It's pretty clear to me that, at some point, if we survive, right, that we're going to be completely different than how we were. Now, is it our goal to go to these other worlds? I would say absolutely. If we find planets around Alpha Centauri, NASA will come down to people at JPL and say, build a little spacecraft and send it there. We want pictures, okay, and radio it back. So when we travel out, not in our present form, I don't think, because we're carbon-based life. We wouldn't survive. You take us off of this little pond of a planet that we live on, put us into outer space, right, where there's no oxygen, no pressure, poof, we'd be gone. But when we send out little micro, nano bots, yes, I think we will. Yeah. Okay, another question. Now I'm in trouble. Yes.
A more prosaic one.
Okay.
If you have a binary star,
yeah,
and you have an orbiting planet, is it orbiting? Presumably there are various structures.
Configurations, yeah. Right.
Are any of them easy to sustain life? Because it seems there's going to be a massive transition in radiation coming from the planet.
Yeah. So your question is, if you have planets in these binary star systems, could the planets host life? And I think the answer, it depends on the separation of the stars, but the radiation falls off quite a bit. If you lived on, let's say, Pluto, right, or even Jupiter or Saturn, the amount of radiation you'd intercept from the sun would be so small. So having another star like that, I think, would impose a hazard. Yeah. Yes? Where are the best telescopes in the world? It depends. It's not just the telescope, it's also the instrument. But honestly, Hawaii is incredible. I mean, the Keck Observatory, those two telescopes, the Subaru telescope, amazing science that's coming out. We're looking now, we collectively astronomers, at building 30-meter telescopes. So right now, Keck is the biggest telescope in the world, but each of them are both 10-meter telescopes. We're looking at building 30-meter telescopes, right, which are going to, wow, what we're going to see with those telescopes. Well, those telescopes go, I guess one of them will go in Hawaii, yeah. So, okay, yeah. So, go Hawaii. Yeah, I mean, that's what I love about this island. I think, down under the oceans and the geology of this state, and then, the mountaintops that look up into the skies. This island, our islands have it all. Yeah. Okay, well, if you guys have other questions, I'll stay and I'd be happy to chat with you a little bit more. But yeah, thank you very much. Great questions.